Okay, so it's also recording. And this screen is being shared. Let's go, first of all, I'm going to do a little drawing on the board, using paint as my whiteboard here. Talk about functions, and I got a little drawing pad. Gives me a little better resolution here. We'll see how this works. Thinking about functions and compositions of functions. And just general ideas about functions. Suppose I have a function. I'll start with a function named g of x. Oh, gotta put the pencil on. I have a function g of x. And let's define him with a certain value. Let's do something interesting here. How about we'll do x over x minus 1. And let's think about now, what are the possible inputs to x, also known as the domain? What are the allowed inputs to the function g of x? Help me out here. Who can help me with what are the possible inputs to g of x? Can I give it all values of x? Is it possible? Can I give any value of x into g of x? Or is there a limit on my domain? What can g of x take for an input? We got a problem down here. There's only one problem. I'm not allowed to divide by 0. So what value can I not have for x? I can't have a value of 1 for x. X can never be equal to 1, or I'll be getting 1 divided by 1 minus 1, which is 0, it blows up. Can't divide by 0. So the domain is something like this. Negative infinity up to, but not including 1, in union with anything greater than 1, all the way up to positive infinity. That would be my domain of the function g of x. Domain is his input. Remember, the domain is the input into that function g of x. So always check the denominator when you're given a function. We know that we can never divide by 0. So here's the proper domain for the function g of x. Well, let's make another function, a little more, I'd say a little more interesting. Let's make another function called f of x equals, or is defined as, sine of x divided by x. What's that going to look like? Well, let's think about what that would look like. As x is a very large negative, we know sine of x is always going to be between -1 and +1. So this is going to go negative, positive. But x, as it gets very large, when I divide by something very large, I get a very small number. So I'm going to have something that looks like this. In the negative side, it's going to be very small. As I get closer to 0, it's going to do something like this. And then it's going to get larger and larger. Sine approaches 0, but x also approaches 0 from the negative side. Sine approaches 0 from the negative side if you have a negative angle. So it looks like it gets really close to the number 1, but can we ever let x equal to be 0? No, no, no. Even 0 divided by 0, even though you might think, well, 0 divided by 0 should be equal to 1. No, you cannot do 0 divided by 0. That is not allowed. So sine x over x looks like it does this. Approaches 1, but we can't say the domain of sine of x over x. What's its domain? Well, it's negative infinity up to but not including 0. And then on the other side of 0, all the way to positive infinity. And there's our function f. So then after After we pass 0, sine of x over x does something like this. Gets smaller and smaller and smaller as we get large x, because the dividing by a large number makes this get very small. So this is kind of a fun function to look at and actually try to graph. It will look like it ought to go that defined at the value of x equals 0. We should say, well, since on both sides it approaches 1, let's just say that for this special function, when x is 0, let's just say it's equal to 1. We could try that, but the mathematicians would say, no, that's not allowed. Even if it looks like it goes close to 1 divided by 1 and approaches 1, we cannot mathematically define it at x equals 0. So the domain is those numbers. Anything but 0 is the valid domain. Remember, the domain is just what the input is for that function. Input value of x. That's what the domain is. So 2 functions, sort of interesting. And if we graph this one, let's just for fun graph g of x. Come down here, let's see, g of x. X over x minus 1. Well, when x is really, really big, it's going to approach the value of 1, right? X over x. And when x is really, really small, it's going to be negative very large number, or another negative very large number. So it's also going to approach 1. But as we get close to the value of 1, right here, interesting things start to happen to g of x. This is g of x. As we get really close to 1, well, that number at the bottom gets really small. X is still 1, and the very small number is a positive very small number. So it gets very large as I get close to 1. So g of x is going to go sky high and head towards infinity right at the value where x is 1. We can never have x be 1 because we'll be divided by 0. Got this interesting thing that happens at the value of when x is equal to 1. The function g of x approaches a very large number. What happens on the other side of 1? Well, smaller than 1 minus 1 gets a very tiny negative number. X is still 1, so it's a positive number. So suddenly g of x is on the other side of 1 here is a huge negative number. It's 1 divided by a very tiny but negative number. And then as I get very large negative numbers, g of x approaches the value of 1 as I get large infinity in that direction or infinity in that direction. But it's always just a tiny bit less than 1. This is going to be slightly more negative number than this as I go large negative number. Just 1 less than this negative. So very close to 1 as I go to negative infinity. Very close to positive 1 as I go to positive infinity. So that's g of x. Okay, that was just practice at what the domain is. Thing to remember here is the domain of 1 says, okay, anything but the value of 1 here is the domain, the input for g of x. And the input for this is any number except for 0 for the input to f of x. Is that making sense? Sine of x, we know, can take any number and it just keeps cycling between -1 and 1. Now, a bigger challenge here. Let's go further down the page, and that's the cool thing about Paint. I can make my page as large as I want. If I go further down the page, now let's think about the composite. That's what this chapter is about. Now I'm thinking about f of g of x. There's one way to write it. To write it this way, it's the same as f circle g or f composite g of x. I like this way better myself. I like to write it out that way better. F of g of x. We call that f of g of x. Or f composite g of x. I just like to say f of g of x. Now, what is the domain of f of g of x? Well, it's the combination of the domain of g and the domain of f. What is the domain of g? Well, all x except for -1. So the domain of g is, I'll just state it in a simpler way, x cannot be equal to, not -1, x cannot be equal to 1. X is not equal to 1 for the domain of g. Well, what's the domain of f? Anything but when its input is equal to 0, right? I can't take an input of 0 to f. Well, we know that f cannot take a 0, so the input for f into f cannot be equal to 0. Okay, so what I have to figure out is, when will g of x ever be equal to 0? So composition of f of g of x means g of x better not be equal to 0, because that's what we're feeding into f of x here in the composition. So now I have to go back and figure out, for what value of x do I get a 0 when I feed it into g of x? Well, when do I get 0 out of g of x? Can you tell where? It's a fairly simple one. When x is 0, g of x turns out to be 0. So that was an easy one. 0 divided by -1. So I know for g of x that the value of x that gives me 0 is 0. Therefore, the domain of the composition f of g of x is any values where x is not equal to -1, or sorry, not equal to 1, and x is also not equal to 0. But see how I had to figure that out? I had to figure out, I know f can't take 0, so therefore there's an illegal value of x whenever g of x, we got to make sure g of x is never equal to 0. Well, that means that x can't be 0. That's because g of x is a simple function, x over x minus 1. So see how we have to figure out, we have to go backwards, what value of x will make g turn out to be 0, because f of x can't take a 0. So composition of functions, that's where they get a little more complicated, a little more confusing. But by working through little problems like this, I'm hoping that composition will be a little more understanding to you. Does that make sense? What I just did, I made two functions, f of x and g of x. And remember, whenever you have f of g of x, that means the output of g of x, That's what feeds f. That's what becomes the input into the function f, the output of the g. So what's another term for the output of g? It's the range. The range of g.
We'll actually get into like some actual problems using kind of like the foundation of some of this stuff, right?
Yeah.
So I think it'll make more sense then.
Yeah.
Right now, just seeing all the, just like the variables or whatnot is kind of.
Yeah, and that's the challenge of algebra is you're abstracting the problem and talking about this theory, which actually problems. That's where it helps. It's more helps to understand why they're doing all this. So we're throwing the terms at you, and one example with two functions, g of x and f of x, just picking an example. But as we do more problems like this, it'll make more sense. And that's what I found. You just have to kind of work through problems using these ideas, then it'll make more sense. And one way to do that is, let's look at the worksheets. Let's look at worksheet 3.1 and work through those problems, keeping this in mind. Whenever I have f of g of x, I'm basically taking the output of g and feeding that into the input of x. All right, so let's take a look at an example. I'll go to my worksheet number 1. Now that worksheet number 1 is there on Moodle. Oh, and I have a hard copy here. If you want to do a hard copy here, worksheet 3.1. It's a fairly simple one. We have a hard copy here. Online, here's what I like to do online. Let me show you what I like to do. If I go online to that, if I go down to worksheet number 3.1, those of you online, you can download that and print it, or open it and print it, but you can also do this. If you have a decent way of writing with your mouse, you can open the document here, on this link here, that will take you to the Google Doc. From here, you can, once it loads, you can print it, and I'm going to print it to a PDF. And you can save that as a PDF, and so I've saved it there as a PDF. And then you can just go open that PDF if you want to work on it online. You can actually open that PDF. And if you're decent enough at drawing with your mouse, or if you have a little pen pad like I have, I can actually draw on this and then save it after I've drawn on it. So I'm opening this now with a PDF viewer that allows me to draw on it once it has opened it. I don't know why it's taking so long to open this file. Here we come, here we come. I can zoom in and out on this, and I can add notes to it. So I'm going to add notes to this as I work through this function here. Now this, we have a couple different ways of looking at these functions. These are not compositions of the functions. You can think of this as taking combinations. Instead of doing f of g, this means function f plus the function g. Well, let's see what they mean by that by drawing it out. Let's see if it lets me draw it out. Yes, here's my pencil. Okay, so f plus g, if I have this as f and this is g, well, this is a lot simpler than composition. It's just simply x squared plus 11x plus 30 plus g, which is x plus 6. F plus g is easy, but they've even made it easier. I don't even have to do this whole equation. I can just set a value of 0 for x and even do it an even easier way. F of 0 is 0 plus 0 plus 30. Well, 30 plus g of 0 is 0 plus 6, so 36. And we started this Friday, so this is kind of review for you. I don't have to do all this, although if I would like to, I can say, well, I know the f plus g would be x squared plus 12x plus 36. But I don't even need to do that. If I'm asked to evaluate it at a particular point, especially when x is 0, that makes it so easy. I can just say, oh, when x is 0, I know what I get out of this function. I know what I get out of this function. So let's do the same thing now for f minus g of 5. Well, f of 5.
So can you always, it's like for like b, where it says 5, 5 is going to be what you plug into those x values?
Yeah.
Okay.
Yeah. So f of 5, I could though, I could say, well, let's look at it both ways. Let's find which one is easier. I know that f minus g is going to be x squared, let's see, plus 11x minus 1x plus 10x plus 30 minus 6 plus 24. I know that f minus g of x is this. But if I only care to evaluate it at a specific value, I can just say, well, f of 5 gives me 25 plus 55 plus 30, which gives me 80 plus 30, 110. And I know that g of 5 gives me 11. F minus g of 5 gives me 110 minus 11 equals 99. If I just say, well, I'm going to figure out the formula for f of g, or f minus g, I get 25 plus 50.
Why did you get that 11?
G of 5 is 11.
Yeah, how did you get that one? How did you get that 11?
Since g is x plus 6. So g of 5 gives me 11.
Oh,
Okay.
okay.
Did I get this wrong? 80, 110. F minus g x 25 plus 50, that's 75. Yeah, 75 plus 24 gives me 99 if I feed 5 into this one. But I don't have to do this. I don't have to calculate and simplify f minus g. I can just evaluate f at 5 and evaluate g at 5 and subtract that. Perfectly fine to do it that way. Now, f times g at -2 is the same as f of -2 times g of -2. Well, at -2, I get -2 squared, which is 4, plus 11 times -2, minus 22, plus 30. So 4 minus 22, or 30 minus 22 gives me 8. 4 plus 8 gives me 12. G at -2 gives me -2 plus 6, or 4. And now multiply them. 12 times 4 gives me 48. So 12 times 4 gives me 48. So f times g at -2 is 48. Now, if you want to make that harder and multiply x squared plus 11x plus 30 times the quantity x plus 6, multiply that all out and get you x cubed plus 66x plus 30x plus 6x squared plus 180. You could then feed a x of -2 and you get the same answer. But it's a lot more work at that point multiplying f times g of -2. So this one, it's easier just to evaluate at -2, each one at -2, and then multiply them together. It'll make your life a lot easier. You don't have to go multiply them out and figure out algebraically what's the multiplication of f times g. Unless somebody said, graph the function f times g of x, then you could feed that into some function that then multiplied it out for you. And if they said, you know, give me the algebraic equation or the algebraic simplification of f times g. But no, we don't have to do that for this. Just evaluate f at -2, evaluate g at -2, and multiply them together. That's what that means. Figure out what f is at -2, then figure out what g is at -2, multiply. So there's my answer for that one. Same thing for this one. I don't have to go and algebraically simplify f of x divided by g of x. All I have to do is figure out what is f at -1. Well, f at -1 is -1 squared, which is 1, plus 11 times -1, which would be -11, plus 30. Or 30 minus 10 equals 20. G of -1, oh, an easy one. G of -1 is -1 plus 6 equals 5. F divided by G at -1 is equal to 20 over 5 equals 4. Just giving you some practice. This is what I would call combinations of functions, not composition. I am doing mathematics on the functions, subtracting, adding them, multiplying them, dividing them. We don't call this, I don't call this composition. I call this mathematical combination or operations, mathematical operations with two functions. Just take whatever you have for f, divide it by g. You could say f divided by g is x squared plus 11x plus 30 divided by x plus 6. Don't worry about needing to simplify that unless they really want you to. I know that that's equal to x. I can tell that, you know, 5 and 6 added together give me 11. 5 and 6 multiplied give me 30. So I know that's equal to x plus 5 times x plus 6 divided by x plus 6. Oh, by doing that, I realize f over g simplifies to x plus 5. And feeding -1 into that, I then indeed do get 4 when x is -1. But this is cool. I've discovered that f over g of x simplifies nicely. And knowing that, f times g of x gives me something interesting too. But you know what? I don't have to figure that out. All I've been asked to do is evaluate it at one specific place. If I had to do a lot of evaluations at multiple values of x, then discovering this would make my life very easy, save me time rather than multiplying this out every time to figure out the answer. If it simplifies to that, I can tell that f over g of x has turned into a linear function. So basically what we're doing here is exercising your skills in algebra in a more complicated way, building up your strengths at understanding and working with algebraic equations. More combinations rather than composition. Let's go ahead and now analyze these for a little practice. So f plus g, this time though, notice we're not given a specific value, so we do need to add them together with the general form, not knowing a specific x. So let's just add them together. X squared minus 4x minus 5 plus x plus 1. Well, simplify that. These two turn into negative 3x minus 5 plus 1 becomes a minus 4. So x squared minus 4x plus 1x gives me minus 3x. And minus 5 plus 1 gives me plus 4. Now, do we have two numbers that when added give me negative 3 and multiplied give me 4? No, but they're not asking me to factor that. We just simplify that out. F minus g, same thing. X squared minus 4x minus 5. And this one you have to be careful. Watch the sign. You're subtracting the quantity x plus 1. Don't forget, you're subtracting all of g of x. And so it's easy to forget you're also subtracting 1. You're not adding 1 back. So it helps to put those in parentheses if you're running into this. Then you remember that it's x squared minus 4x minus another x minus 5x minus 5, and then doing another minus 1 because it's that minus, the 1 is inside there. So that becomes minus 6. And if I want, I can see, let's see, that would that factor into x minus 6 times x plus 1. If they asked you to to factor it, I could also recognize that that's the same as x minus 6 times x plus 1. Either answer here is okay because they didn't say factor it, they just said simplify. If they said factor if possible, then this would be the correct answer. And if I recognize the factoring, it's helpful sometimes to recognize that, oh yeah, that's the factoring of that gives me that. Why is factoring helpful? Well, it helps you to quickly see that when I have x is equal to 6, I know that it turns out to be 0. Knowing where the zeros are is often very helpful to figure out and know the behavior of the function. That's where it crosses the x-axis. When x is 6 and when x is negative 1, and I know it's a parabola, that's going to get larger. So I have a parabola like this. It crosses at 6 and negative 1. So knowing that, I can more easily graph that. Have a question?
Yeah, so like for the 2a, x squared minus 3x plus 4, should we have like factored that one too? Like if we get that, or
You don't have to. I only factored it just for fun.
just to show that
Yeah.
you can? Okay.
This one, I didn't see a factoring jump right out on this because I don't think there is.
All right.
So I didn't. This one I recognize, oh yeah, minus 6 plus 1 will give me that.
All right.
That's the only reason I did that, just because it jumped out at me.
Sure.
If they had said simplify and factor, now this one, if I couldn't factor, my only option is to feed it to the quadratic formula, and I have to do negative b3 plus or minus the square root of b squared 9 minus 4ac minus 4 times 1 times, yeah, so I get a negative number there over 2a. So that is never going to hit 0.
Alright.
So there is no solution of this equals 0. So there is no zeros.
So like CBF or something like
Yeah.
cannot be factored.
Cannot be factored. Yep.
And then if you were really breaking down B, would you leave it where it's at, or would you say like x is equal to 6 comma -1?
I would leave it at either of these. I would leave it at that, actually. This is the most
Sure.
simplified. If you prefer, I would accept this as an answer, just it shows more work, but you
Right.
don't have to do that.
Okay. Thanks.
If they say, now what is the domain or what is the range? The range is, well, it's gonna get, what's the smallest it's gonna get? Well, at negative, at 3.5, no, at 2.5, it's gonna be at its minimum. That would tell me what the range is, but they haven't asked me that. Multiplying it out, this one gets a little tougher because I do have to do the multiplying since there is not a specific value. So we better just go through the work of multiplying it. Put the parentheses in here now because you're going to be doing some multiplying. X squared minus 4x minus 5 multiplied by the quantity x plus 1. So let's multiply x by everything and then multiply 1 by everything and add them. So everything multiplied by x, I get x cubed minus 4x squared minus 5x plus x squared minus 4x minus 5. Now, I get an extra x squared and I get a extra minus 4x. So x cubed minus 4x squared plus x squared minus 3x squared minus 5x minus 4x minus 9x minus 5. And I'm not going to worry about factoring that. But I know when x is 0, it's going to be at -5. But it's going to be cubed, and so it's going to be, I know when it's cubic, let's see, it's going to be -5 at 0, and then it's going to keep getting bigger and bigger. It's going to look something like this. But they haven't told me I have to graph it. Just generally, we know what cubics are going to do. They're going to have a little twist in them. Going to go large negative and large positive when I go to plus or minus infinity. F divided by g.
How did you get x to the power 3?
Which one?
The x to the power 3.
Oh, x squared. See, I multiply everything by x. X squared times x minus 4x times x minus 5x. So the x cubed is this x squared times that x.
Okay.
That's where I get the x cubed. So think of this as x times all of this plus 1 times all of this. Now, factoring it will help me do this one. So let's factor f. This is where factoring f will help me simplify this. See how x squared minus 4x minus 5 is the same as, let's see, x minus 5 times x plus 1. Divided by g, which is x plus 1. Here is where simplifying or factoring does help me simplify. I see that dividing by x plus 1 gives me x minus 5 for f over g of x. But there is one problem that I have to pay attention to. Remember, I can never be dividing by 0. So even though the g cancels out, g can never have a -1. So I have to say x can never be equal to -1. even though g divides out, since g is undefined, well, g is 0 at x equals -1, I can't do 0 divided by 0. I have to specify, although they didn't say I had to specify my range. It's helpful to remember that since g is 0 at a value of -1, I need to specify f over g of x can never take a -1 for a value. Even though 0 divided by 0 seems like it ought to cancel out. If I'm saying I am dividing by g, I have to say, wait, I can't divide by 0. I have to specify x is not equal to -1. But mathematically, any other value of x, it simplifies to x minus 5. So without composition, the problem is generally a little easier. Again, we're just doing combinations. This time, only f plus g of x. And after simplifying, we're just simplifying. What do we simplify f plus g of x? Well, they've given us a pretty easy one. Since we have room, let's go ahead and we'll do the adding of them together. And I'll put them together. Since I know I'm adding them, I'll start with the highest powers first. So I know it's 3x squared plus 2x plus 2x plus 2. I decided to add g first. And it is okay to change the order when you're adding. So that becomes 3x squared plus 4x plus 2. Doesn't look like I can simplify or factor that. They didn't say I had to factor, so I'm not going to. It doesn't jump out at me as being factorable since I have a 3 there and a 4 there and a 2. So good with that. All right, next one on the next page. Now we're multiplying them out. F times g of x.
You go back up to that.
Oh, sure, yeah.
Okay, thank you.
It turned out I was moving it.
Yep, that works.
Now we're simplifying this one. There notice we're not doing composition yet. We're still just doing multiplying the two. It's not the same as f of g of x. That's coming next. That's the harder thing. We're not doing that. We're just multiplying them out. So we're just doing 2x plus 3. I'll put it in parentheses, times, well, yeah, I'll multiply them out. 4x squared plus 2x. I could factor out a 2 just for fun, and that gives me 2x. And I could factor out a 2x. So I get 2x times 2x plus 3. Let's just see how that turns out. I got a 2x here times, so it's 2x plus 3 times 2x times 2x plus 1. Does that do any good for me? I've sort of factored it, but let's multiply it out and get the full polynomial. So 2x times everything over here. So 2x times 4x squared plus 2x plus 3 times 4x squared plus 2x. Now multiply that out. 8x cubed plus 4x squared plus 12x squared plus 6x. And I have x squareds combining. (16x squared) plus 6x. Now, if I want to factor that, notice that 2x comes back out. I can factor out to 2x. And I know it'll factor, it'll factor back out. Will it Control Z? Let's see if a Control Z undoes that draw. I'll do the little, I'll just leave it. So this is the multiplying out. They didn't say to factor, so I'll just leave it here. I could factor out a 2x if I wanted to. Should we factor out 2x just for fun? 2x times 4x squared plus 8x plus 3. That simplifies it somewhat, I guess. If I did a full factoring, this would give me the full factoring way back up here. So I'm not doing f of g of x. That's a whole different monster. F times g of x is that. And I would probably take either of these. These are both valid answers. This one I just multiplied it out. This one I started doing a little bit of factoring. Here I did the complete factoring. If they say factor, then this would be the factored solution. And see how I got that very early. Sometimes this is actually more meaningful because I know where my crossings are. At x is 0, at x is -1/2, and x is -3/2. Yep.
So why couldn't you just like from the get-go done like the 2x times 4x squared, 2x times 2x? Like did you have to necessarily like factor it and like extract it?
No.
Okay.
I just did this just for fun, recognizing, hey, there's a 2x multiplying by those two things.
All right.
I can very quickly get to the factored form.
Sure.
Multiplying it out takes me actually a little bit more work.
Right.
So this is more work,
Wait, gotcha.
but it just gives me a different form.
Sure.
Sometimes when I want to graph it, I'd say I actually like the factored version the best because that tells me a lot more about my function. But I'd say simplifying, they want you to multiply it out. So they're probably, the fewest number of variables. This is the standard polynomial form. So if they clarify and say simplify to, multiply out to standard polynomial, this would be what I would leave it as. Now a little graphing, completely you can't put this in a polynomial. They're straight lines, they're segments of straight line. And fortunately, we don't have to give the function of x. They just want to evaluate at a specific value. So all I have to figure out is what is the value of f at 0. So f at 0, let's see, this is f, this is g. F at 0 is 0. So that's basically f of 0 plus g of 0. Well, f of 0 is 0. G of 0 is 3. Therefore, 3. So all I do is find based on my input. Remember, this is my input. This is my x. So whatever's in the parenthesis, I look along that line for my input at that point. So now, this is f of 4. It's g at the value 4. Well, what do I get? F at 4 is this, is 4. G of 4, come out to 4, is this. 4 minus, and watch your sign, 4 minus a negative 3. That's G at 4. So therefore, that equals 7. Always, if you have any sign issues, and you still have, I still have sign issues when I get problems like this, throw the parentheses in there to remind you you're subtracting a negative 3. It's so easy to forget about that and get the wrong answer. F times G at negative 1, again, is just F, whatever at value of negative 1, times G evaluated at negative 1. Well, F at negative 1 is a 2. G at negative 1 is a 1. See, I go to wherever the input to G is negative 1, figure out where that graph is crossing. And now, F of 1 divided by G of 1. F of 1 is there, equals 2. G of 1 there is 2. Just giving you practice at evaluating the combination of F and G. Now think of this practically, the whole reason we're doing this is we may have a complicated function. We know F and G, and we discover something else about the data. That when I divide the data, I'm getting something different in terms of the physics or in terms of the actual word problem. If I can simplify my work, it's easier to figure out F and then figure out G, and I know some physical law or some chemistry law that I know that when I divide the two, I'm figuring out the chemical reaction or how that mechanical device impacts the other device. If I know that when they do that certain thing, it's the same as multiplying the two functions, I've solved a hard problem that's a combination of two smaller problems. Now, I don't have those problems yet. I'm just doing the math part of it. But out there in the real world, as we use our math, if we know that multiplying two functions together is the same as like the chemical reaction, well, if I know that something about that first reaction, something about the second reaction, by doing all the research, I've discovered a harder problem multiplying the two together. So the whole idea out there in the world, you can find a combination of some mathematics or physics or chemistry, they become some function F and G. We can solve a larger problem using our math skills, combining the solution or dividing and conquered. I have F and G, or I find a hard solution and I realize it's a combination of two smaller ones we already know about. That's the whole idea of math, is you break in a hard problem into smaller pieces, or you take two smaller pieces and you solve a harder problem. You can go both directions. So that's the practice in that first worksheet, just getting an idea of evaluating F and G at a particular value of X, and then combining them. Now let's go on to the harder problem of composite functions. Now, I talked about that at the very start. Now let's do a worksheet of that. And the worksheet I have over here, downloaded already, worksheet 3.2, and I think I have a hard copy here for you. Thought I print out. Yep, I did print out worksheet 3.2. So online, you can either print a PDF and scribble on it, or print a hard copy and write on it by hand. Now we're doing composition. And again, starting simple and then going to the more complex. So let's bring up 3.2, worksheet 3.2. And just to remind you here, the plan for this week, back here at Moodle, where'd my Moodle page go? Here, the plan for this week is here in the assignment schedule, and I've tried to make sure the dates on things are coming out right in Moodle. The plan for this week is to finish section 3132 and have you work on quiz 6 for next week. So today, mostly working on 3.1. We'll get started on 3.2, and then we'll practice more on Thursday, and maybe even give you some help with quiz 6. So you're welcome to, I think you get, I forget if you get a couple tries at quiz 6. But this is our plan this week, getting 3.1 and 3.2, and get a good understanding of that. All right, so let's get started on 3.2, and we'll do more on Thursday as well. So come back to here. If you print it out and then edit the PDF, I'm here in the PDF. Now it's time to look at the composition instead of the combination. So remember that dot. I'm going to write it out the way I like to. I like to write it out this way. When I don't like to write it out this way. I like to write out F composition G of X. For me, if for some reason, I like to think about it this way. I take F and feed G into it. I like thinking about it this way. And I like to call it F of G of X. That's how I pronounce it. F of G of X. I don't like to say F composition X. F of G. Whatever G generates, G feeds F. I figure out what G gives me, and the output of G goes into F. That's all that means. So F of G of 10 is the same as, well, let's figure out what G of 10 is, and then we'll figure out what to do with the output of G. So let's figure out is equal to, well, G is 3x squared plus 4x. So it's 3 times 10 times 10, 3 times 100, plus 4 times 10, or 40. So 340. Now I take 340 and feed that into F. So F of 340 equals 2 times 340 plus 5, or 685. So F of G of 10 means evaluate G at x equals 10, gives me 340. Feed 340 into F, and then solve. That's all that means. Take the output of G, and that feeds 340. And we'll be doing more fancy things, evaluating it as a polynomial, but for now, just take the output and feed it into F. Now it's going the other way now. We have to figure out F of 11 first. So the thing on the right is what we have to figure out first. Because remember, G composition F means G of F of 11. So we have to figure out F of 11 first. Well, F of 11 is 22, 2 times 11 plus 5 equals 27. Now, I might need my calculator here. I need to figure out 3 times 27 squared plus 4x. So G of 27 equals 3 times 27 squared times 27. And I got to go to my calculator. I have one here somewhere. Calc 84 app I found. I think that works. Let's see, so it's 3 times 27 times 27 plus 4 times 27 equals 2295. Couldn't do that one in my head. 2295. Now this looks weird. What do you mean f of 8? Don't let that scare you. Just pretend that that's, two different functions. That just means f fed with, well, f of 8. Figure out what f of 8 is and feed it back into f again. So f of 8 is 2 times 8 plus 5 equals 16 plus 5 equals 21. Take 21, feed it into f again. F of 21 equals 2 times 21, 42, plus 5 equals 47. So I just take f, evaluated at 8, whatever that gives me for output, feed it back into f, giving me f composition of f. I like to just say f of 8. And there's my answer. Now the composition gets interesting. Oh, wait a minute. I was doing the wrong one. I've actually made it a harder problem. We'll do the harder problem now that I started. I wasn't paying attention. Table below. We'll come back and do it from the table below. I'm having too much fun with it. So g of g, it would be g of 15. That's why I'm thinking, wait a minute, they give you hard numbers here. Well, g of 15.
Yeah, I'm good with this last one. It's crazy big.
G of 15 is 3 times 15 squared plus 4 times 15. Well, let's figure that out. Since we got on this track, I'll just use my calculator. Clear. 3 times 15 times 15 plus 4 times 15 equals 735. Uh-oh, now it's going to get huge. Now, g of 735 equals 3 times 735 squared plus 4 times 735. Well, since I have my calculator, it's not that hard to do. So 735 times 735 times 3 plus 4 times 735 gives me 1,623,615. Now we'll do the easier way. Now that we've done that, these other problems are going to be so easy. 615. Now that you've done a super hard problem, realizing now, wait a minute, they didn't mean this function, they meant the table below. Let's see how much easier that will be just using the table below. Well, here's what we do. For this first one, let's see, I guess we'll start it here. For A, f of g of 10, well, means, let's figure out what g of 10 is. G of 10 is g of 10 is 8. So f of 8 then is, here's input 8, I get 14. F of g of 10. So there's my A answer. A lot easier than that. Now, g of f of 11, g of f of 11, well, f of 11 is 8. And g of 8 is 14. So there's that answer. F of 8 is the same as, well, f of 8 is 14, is the same as f of 14. And f of 14 is 10. And now the last one, g of 15 is equal to g of, let's see, 15, feed it into g, I get negative 4, is the same as g of negative 4, which is equal to negative 4 into g gives me 12. Way easier than all of this. That tells you to pay attention to the instructions. Table below, I jumped right to this, ignoring the table below sentence. Gave myself a lot more work than I needed to. So there's A, B, there's C, that's B. A, B, C, D answers. So combination, remember all that we're doing here is we're taking the result of that second function, feeding it into that one. So what I like to do whenever I see that, for me to get it right, I always turn that into f of g of 10. That helps me remember that I have to figure out what's inside here first. Then I feed that into f. That's what that f dot g means. And remember, that's not the same as g of f. Sometimes with special functions, f of g gives you the same of f or g of f. But most of the time, it's not reversible. The opposite is usually not the same. There are some special functions that we're going to talk about. The inverse function, when you do f of g of x, you get x back. That means f and g are inverses of each other. F will reverse what g did. Those are special functions that have special relationships. If you get x back after doing f of g of x, then you know f and g are inverses. So now let's look at one more here. Now they want us to calculate out, and they've given us not super complicated functions. Let's write that out just for practice. Composition now. Now we're getting into the meaty stuff here. So f of g of x. Be careful you do it in the right order. G of x goes where the x's are in f. So take g of x, and I'll write it out. That means I take g of x, and I square it. Okay, so I get x plus 1 times x plus 1, x plus 1.
How did you know to square it again?
Because f of x is taking its input and squaring it. And now I'm adding plus 3 times its input, which is g, times x plus 1. This is f of g of x. I take g of x, which is x plus 1, and I feed it into f of x. So wherever I see an x, that becomes x plus 1. So x squared becomes x plus 1 times x plus 1. 3x is now 3 times x plus 1. And now let's go ahead and multiply it out. X squared plus x plus another x plus 2x plus 1 plus 3x plus 1 equals x squared plus 5x plus 2. There is my f of g of x. Wherever I see an x in f, I put what g is where that x was. So x squared becomes this plus 3x becomes this. So x plus 1 gets multiplied by itself, and x plus 1 gets multiplied by 3. That's what the composition is. Let's do another one then. G of f of x, we go the other way. G of f, well, g is take whatever it has for input and add 1 to it. Okay? So g of f of x, well, what's its input? Its input is g of x squared plus 3x. Well, whatever I give for input, what do? I add 1 to it. X squared plus 3x. There's my x squared plus 3x plus 1. So you can kind of write it out this way. Whatever I feed into g gets 1 added to it. And so there's my answer. X squared plus 3x plus 1 is g of f of x. And they're definitely not the same thing. X squared plus 3x plus 1 or x squared plus 5x plus 2. F of f, well, I take f, feed to it the function f itself. Well, I take whatever I'm given, square it, and multiply and add multiplying by 3. So x squared plus 3x squared plus 3 times x squared plus 3x. Now, don't panic. Let's just multiply that out carefully. That's x to the 4th, x squared times x squared, plus 3x cubed, plus another 3x cubed. I'm going to get 6x cubed. So I'm going to get 3x times x squared plus the outside 3x times x squared. Give me 6x cubed. And then 9x squared. And then multiply out the 3 plus 3x squared plus 9x. Now I have 12x, total 12x squareds, and give it a complete polynomial now. X to the 4th plus 6x cubed plus 12x squared plus 9x. Normal polynomial form. I do see that there's an x that's a factor of everything, but they haven't said I had to factor it. This would be an acceptable answer. And it's time to end. We'll continue this and practice more composition next time. We'll end this recording and let you have a great Tuesday. The recording will appear